Right, well, yeah, thanks to the University of Tasmania, the Fire Center, and David for the invitation and to host us. We're here during your summer, and I'm very grateful to not be shoveling snow back in the Northern Hemisphere. So this is a privilege. I'm also going to be experiencing 3 summers in a row, 3 fire seasons in a row. I study climate change. I study longer fire seasons. I'm living this, apparently. So as David mentioned, I operate in the realm of meteorology and climatology, but also more of my recent research has delved into more applied questions in terms of how meteorology and climatology impact natural resources in society, including fire. And so what I'll do today is give you basically a little bit about 2 papers that I published fairly recently in the Geophysical Research Letters that exemplify the very, very different spatial scales in which the atmosphere can influence fire. So for this first study, we're going to put on our detective hats, and we're going to solve the case of pyrotornadogenesis. That's a hard word to say. I'm probably going to mess it up a few times. I'm Greek, so of course we know that all words come from Greek origin. Maybe? No. So pyrotornadogenesis is actually a combination of Greek and Spanish, and it means either the birth of a tornado from a fire or the birth of a fire from a tornado. Both are pretty cool, right? We're going to focus on one event here, an event that occurred this past summer in July in Northern California on the so-called Carr Fire, where we saw a very large fire vortex develop. The vortex was developed in the evening hours from around 7:30 to 8 p.m. local time. It moved around 1 to 2 kilometers, and the diameter of this vortex was on the order of 300 meters. So this was not your run-of-the-mill little fire world. This was a pretty significant event. We know that there are fire vortices. These are not a novel thing. They happen at a variety of scales. We see them in labs. We see actually fire columns that develop in situ along a fire front, and we can see also larger fire whirls that develop that are on the order of tens of meters. They form from the bottom up. So purely tornadoes actually can form from the top down. Fire whirls are a little different. They're in the similar camp as sort of dust storms or dust devils, or I don't even know what they're called in Australia, but you probably know what I'm talking about. And they're basically formed due to the buoyancy of heat release at the surface. There's obviously a good heat release at the surface from a fire, along with some sort of turbulence in the atmosphere that can be induced either vertically, wind interacting with terrain, as shown to this example on the right. The combination there is you get heat release, you get spin or vorticity in the atmosphere, and it's sort of self-supportive for some time. So why do these vortices matter? They're obviously quite interesting and fascinating to look at. They personify fire as if fire didn't need to be personified. But they obviously matter from the perspective of bringing about pretty volatile conditions in terms of fire behavior. And you can kind of see these actually play out in the video in terms of the rotation, the wind speeds, the lofting and long-range spotting of embers. You basically have the sort of the wicked combination for really, really devastating fire behavior. And our question that we're going to tackle here first is, was this a tornado, right? It was impressive, right? It was spinning, but was it a tornado? Did it have tornado-like characteristics? And so part of this is actually understanding the event and then trying to go and understand how we define a tornado and then see if the characteristics match or not. This is not the first case of a very large fire whirl or even a pyrotornado. The first well-documented case, there are probably other cases out there. People talk about them anecdotally. But the first documented case here was in Canberra in January of 2003. This event occurred during extreme fire weather conditions, right? The fire weather index was well above the 99th percentile. This event resulted in a 20-kilometer long track tornado with wind speeds upwards of 250 kilometers. You can see visible evidence of this tornado in terms of the plume itself. You can see the vortex. You also can see a pretty impressive pyrocumulonimbus develop, and that went up to around 15 kilometers. And you can also see some pretty interesting signature of the wind throw from the fire and the tornado interacting with the trees going in opposite directions there. So let me give you a little bit of background on the Carr Fire. I'm going to set the stage for it, and then we're going to go and sort of take a top-down inverse funnel approach to look at the climate, the weather, and then sort of the mesoscale information from radar and satellite. No surprise, this past summer was incredibly active fire season for much of western North America. California was hit with a number of very large fires. In fact, they had not only their largest fire on record, but also the fire that caused the most number of fatalities on record. Very active fire season in California. The Carr Fire occurred in the northern portion of California in a pretty interesting location from a biophysical perspective. So this occurred in what we would generally call a mixed forest, transitioning to shrubland and grassland. It's a region that is climatically quite unique. It rains a lot here. This region, in a sort of a normal year, gets 1 to 1.7 meters of precipitation. There's quite a bit of topography sloping down into the Central Valley of California. But most of that precipitation falls in the cool season, and summers are really, really warm, right? The average June, July, August summer temperature is 31 to 35. So not too many places you can find globally where you get the combination of such a strong seasonality and precipitation along with brutally hot and dry summers. The Carr Fire is named for the fact that it occurred on Carr Road. It was started by a car as well, but that would be one R, not two. It started on July 23rd. It burned for about 5 weeks. The fire initially was a terrain-driven fire moving uphill. And then what I'll show you here is that some large-scale synoptic meteorology changed and allowed it to basically move downhill and advance into the wildland-urban interface towards the towns of Shasta and Redding. And Redding, just so that you guys know, it's a town of around 100,000 people. This is not a small town. This is a fairly large metropolitan area that is, again, right there at the apex of a very wet area and an area that gets a lot of heat in the summer. This fire resulted in a total of 8 fatalities, 1,600 structures, and 40,000 evacuations, and at least half of the fatalities occurred with the fire tornado/vortex. So let me show you a little bit about where this vortex occurred. And so if you look at the big picture here, the vortex occurred right sort of along the western edge of the fire as it basically jumped the Sacramento River. This is a fairly large river. This is the main body of water that feeds the northern portion of California. People take a lot of water out of that for irrigation, etc. So it's no small feat that this fire jumped the Sacramento River. It then got into this area where you can pretty clearly see we have an intermix of wildland fuels and structures. So very much it took off in a region where we had very interesting fuels, both homes and vegetation. And basically this polygon here is showing you sort of the swath of where the wind damage occurred from the vortex. And that was, just to give you a scale here again, this is about 2 kilometers that the vortex was on the ground. So just another video here just to sort of show you rotation. You can look at sort of the winds that are sort of circling around. You can potentially see some debris flying. These are things that we look for when we look for a tornado. We're looking for a rotating column. We're looking for debris flying. We're looking for significantly strong winds. And we're looking for the fact that the vortex reaches from the cloud to the ground. So those are basically some of the criteria that we can look at, and you can see some of the embers actually being lofted in these videos themselves. Okay, and this is just a couple pictures here in terms of the damage, right? And this is not the damage from the fire, although those are definitely burned trees there. This is just giving you an idea of the damage from the wind. How strong were these winds? And what happens in the U.S. is that the National Weather Service goes out, and they do a post-mortem after a significant severe weather event. So what they did is they went out and they basically assessed the damage. They're looking for how much damage occurred the scope of that damage, and they can relate that. They use some sort of back-of-the-envelope estimates to relate that to estimated wind speeds. And when they did this for the Carr Fire, they estimated the wind speeds to be on the order of 64 meters per second. And David asked me, what is that in kilometers per hour? And I just don't know, but it's over 200, I hope. You guys can do the math. So very, very strong wind speeds estimated per the damage. And you can see these steel pipes wrapped around trees. You can see basically the roof being taken off of houses. And then, where the fire did burn, it was a scene that you might see out of some sort of action movie in terms of the damage it caused. Okay. So I wanted to give you, again, sort of what was happening here, what was responsible for this fire vortex. And as a climatologist, I typically think of fire as being climate-enabled. Climate provides the setup in terms of fuel availability. And weather does a lot of the damage in terms of driving the fire. So if you're not aware of it, California has gone through a significant drought. They basically went through their worst 4-year drought in at least a millennium from 2012 to 2016. It resulted in severe water shortages. We also, as Crystal and I were coming to Tasmania, we drove through California. We basically saw large swaths of land where trees were basically dead. So you got a lot of standing dead now after this drought. Flash forward to the winter of 2016-2017, and the whole western United States and California was incredibly wet, right? So, oh, look, we got a relief from a drought, right? It's over. Maybe, maybe not. In fact, when you get a wet year like this, especially when you have fine fuels, that can actually accelerate the growth of fine fuels. And then this past winter, very dry in the region, right? So very, very dry. And just for reference, the Carr Fire perimeter is the little black swath here. Fuel moistures declined pretty rapidly. They were well below their sort of climatological levels going into summer. And then July was incredibly hot. It was the warmest month on record for the region as a whole. Particularly notable was the fact that overnight low temperatures didn't provide much relief. And the fact that when you have really, really warm overnight low temperatures, that ends up resulting in a lack of overnight humidity recovery that allows for fuels to continue drying out. And the typical, approaches for fighting fire may not be as successful, the ones that are sort of diurnal in nature. So we'll flash forward here to the 26th of July. This was the day of the fire vortex. This was the day where the fire made a turn. It went from being terrain-driven to actually being forced in towards the city of Redding. It moved to the southwest. This was a hot day, right? And it was not only a really hot day and set a record in Redding, it was also the day where we had the highest mean vapor pressure deficit in 40 years of any day. So an incredibly dry day. This is not a day where you should see a tornado. This is not a day where you should see a tornado with that sort of vapor pressure deficit. Very, very low 100-hour dead fuel moisture values. This is one of the metrics that we use in the U.S. for tracking fire potential. Okay, I'll give you a little bit of the weather. We're going to look at the big scale. So at large scales, right, the Redding is basically where that L is. We had a thermal low situated over central California. This is a pretty typical pattern. When you have warm temperatures, you develop a thermal low. You guys have thermal lows in Australia and the interior in the summer as well. But what was interesting is that we had pretty high pressure just off the coast. And so we ended up having this somewhat strong surface pressure gradient. It's not strong by winter standards, but it is strong by summer standards. And this is actually this strong sea level pressure gradient driving through pretty complex topography ends up forcing a moderate sort of northwesterly wind, right? So that northwesterly wind takes the fire that was burning northwest of Redding at a higher elevation and basically encourages it to move downhill. Okay, and now what I'll do is I'm going to zoom in and I'm going to show you a high resolution regional reanalyses product. This is an operational product used in the United States, hourly estimates of wind, etc. And this is really hard to see, so you'll just have to trust me. So Redding is basically right in here. The fire perimeter is shown in red here. And what we're looking at is we basically have up-valley winds, right? So the thermal trough induces these up-valley winds. And then we have surface northwesterlies coming here. and the two collide, right? Right basically where you see that fire vortex occur. And the colors here is indicating a measure of how much rotation is actually occurring at the surface. And I'll note here that these models don't know anything about the fire occurring. They're just showing you what the weather would be like in the absence of the fire. But nonetheless, what we can say is that there was some background source of spin, horizontal spin, present right at the apex of where that fire vortex occurred. And we know that the fire vortex, specifically when you have this large heat release on a fire front, that's going to create its own fire weather. So the idea here is that the background mesoscale circulation is preconditioning the fire vortex for really occurring in that area. So is it a tornado or not? Let's look at the key characteristics of a tornado. Funnel cloud, rotating, circulating debris, we kind of saw that already, right? Strong wind speeds. At the surface, there's evidence for strong wind speeds. We're going to take a look at whether or not we have observational evidence, because the evidence of strong wind speeds was post-mortem, right? It was looking at the damage. And then finally, was there a rotating cloud-to-ground vortex of air? Well, the videos that I showed you, they're looking at the ground. They weren't looking up, for probably good reasons. But there's no visual evidence that this vortex actually reached the cloud bottom. So we're going to go through and show you some potential evidence. And now we're going to move in and talk about radar and satellite. And this is basically how we can have more definitive proof that this was a tornado or had tornado-like characteristics. So this is a weather radar. It turns out that we had a weather radar located around 140 kilometers south-southeast of the Carr Fire. This is the Central Valley of California, so there's nothing obscuring it, right? Weather radar is not going to work as great, at least for low-level circulations when you've got terrain in the way. Not an issue here. So the weather radar is scanning radially and also vertically, so it's trying to give you sort of a three-dimensional view of the atmosphere, and it's trying to detect hydrometeors and debris. Everything from sprinkles to frogs. And it's also, what I'll show you here particularly is it's also able to give you information about the relative velocity of these hydrometeors, and that's the Doppler effect here. So what I'm showing you here in this image is basically a measurement of the relative velocity of the air, right? And where you see the orange colors, that means that the air is moving away from the radar. The radar is located, basically down here. And the blue means that the air is moving towards the radar. And one of the key things that we look for in terms of severe weather, in terms of tornadoes, is where we see this couplet, right? You see the strong gradient between something moving towards the radar, something moving away from the radar. So that's the key thing we look for, that strong shear there. Okay, this is a busy figure. But what we have here is basically radar scans at different elevations, so 2.5 kilometers all the way down to 5.7 kilometers, right? And then we have time going from left to right. And so the key thing here is that you see, even prior to the vortex forming, we have this background shear, right? So we have this southerly upslope valley flow, and then we have the northwesterly flow that's driving that fire down into the city of Redding. So that background shear is there. That's that mesoscale setup that we had. And then you can see right around 7:30, you see this strong couplet develop. You see it extending up, and it extends up to around 5,200 meters, right? And then there's ambiguity, right? There's this sort of, the weather radar is not giving you the greatest resolution in the vertical, so it's not exactly clear where it stops and where it starts. I'll also mention that we can see debris being lofted up to around 12 kilometers in elevation. So that's getting up there into the stratosphere. And we also have some evidence that there was pyrocumulonimbus. This figure down below here is showing us a time series of basically the estimated wind speeds at different levels. And so just for reference here, the black line is indicating that at least at 2.5 kilometers we had wind speeds, the strongest wind speeds there on the order of 30 meters. So surface wind speeds estimated by the Weather Service, 64, and you can see it actually attenuating a bit with height, which is sort of what you would expect. Okay, a little bit of satellite observations. This is using the GOES satellite product that covers much of the United States and Western Hemisphere. Visible imagery, we have here, we have pretty clear evidence of a couple pyrocumulonimbus clouds developing and then being lofted off to the northeast with the prevailing winds once they get up there. This is a sort of a fire temperature, and you can see basically the fire temperature is maybe an indication of how significantly the fire is burning. You can actually see it really sort of taking off a little bit later. So this figure here is somewhat complicated, but it's trying to put three pieces of information together. One is the blue line is showing you a time series of basically the plume top height, right? So this is when the pyrocumulonimbus develops. And the black line is showing us the wind shear from the radar, right? What we saw previously in the previous diagram. And the red is showing us the fire temperature, more or less. So the interesting thing is that what we actually see is we see the development, rapid development of the pyrocumulonimbus, and that actually helps support the intensification of the wind speed. And this is this concept where we basically get a plume develop, and you actually induce spin. It's, you know, in a very simple sense, this is kind of like the idea of the ice skater, right, who brings her arms in and she spins a bit faster in terms of increasing the rotation rate. So we have some evidence here to say this is a tornado. That last piece is challenging to get at. There's evidence that there was a signature of the vortex up to 5,200 meters. We can do some estimates about where the cloud base would have been using radiosones and soundings and the top of the pyrocumulonimbus. And we basically get some ballpark estimates that it was between 5,000 and 6,000 meters. The reality is that usually tornadoes bring precipitation, heavy precipitation, hail. Very rarely do tornadoes have a cloud base that is below 2,000 or above 2,000 meters above the surface. So this is a very rare event. And unlike the event that happened in Canberra, this event was actually really generated in situ. There was no convection or anything else going on outside of the fire center itself. This was an event purely driven by the fire. It would not have happened in the absence of the fire. So a few key conclusions here. Again, we suggest that there was a shear zone out ahead of the fire that really facilitated the vortex. Really exceptional climatic setup and weather. And there's some interesting questions on, well, we see a lot of pyrocumulonimbus develop. Why don't we see more of these pyrotornadoes? Right? Does it have something to do with the fuels? Right? This certainly moved into the wildland-urban interface. Does it have something to do with the fact that this occurred under, ridiculous fire weather conditions in terms of the fuel moisture, how hot it was, how dry it was? Nonetheless, these are events that we should be looking out for more. And there's some interesting thought here that we might be able to use weather radar a bit more proactively. We use, at least you guys probably do too in Australia, we use it in the United States to identify potential rotation for thunderstorms, but it might be also used on fire to try to identify potentially catastrophic fire behavior, assuming that it's evident in the radar. So I'm going to completely pivot here and go from a local scale feature to the globe. That's the title of my talk, I guess. And this is a paper that I led, which basically looks at the issue of climate change and asks when and where do we expect fire weather indices to emerge from the background natural variability. Okay, and I mentioned that it was a pretty brutal fire season in western North America this past summer. And just one day here of satellite imagery showing you the extent and the widespread nature of fires burning in British Columbia. It turns out that British Columbia had its largest fire season on record this year, besting the record set in 2017. And in fact, some really quick calculations that I did, if I take the area burned in British Columbia, the area burned in western United States, put them together, this is the most fire that we've seen in a given year in at least 50 years. And this is becoming a significant issue. If it's not an individual community being impacted directly by fire, we are certainly seeing the impacts of fire through smoke and its impact on human health. And a funny thing happened during the fire season, and I got a call from the local media. There was a Facebook group out of Spokane, Washington, which is eastern Washington state, just a little bit north of me. And they put together this Facebook event where basically everyone in the city was going to take their box fans to the top of the roof, point the box fans north, and blow Canada's smoke back from whence it came. I was asked to comment on this, and I said that it was not the most asinine idea I had heard for a fire policy this past summer. You can guess what some of the other ones were. So a lot of fire, of course, in British Columbia, a lot of fire in the western United States. And we know that there are very strong relationships between climate and wildfire. And this is a study that I led a couple years ago, just trying to understand how strongly coupled climate and wildfire are at broad scale in western United States forests. And what we found was that if you look at measures of just how dry the fire season is in terms of this term called fuel aridity, a single climatic variable can explain upwards of 3/4 of the year-to-year variability in burned area. It's pretty remarkable. People do talk a lot about, oh, it's all humans, you know, human-ignited fires causing a lot of this. Well, it turns out that climate is clearly in the driver's seat in terms of driving year-to-year variability. And if you look at this figure also, what you'll see is that I've color-coded the dots. Red means post-2000. Those red dots are basically up in the northeast quadrant. And this is no big surprise for us living in the western United States. Things have changed, and things have shifted towards much drier, much warmer summers, and we've correspondingly seen a substantial increase in fire activity. And we've estimated, we did some back-of-the-envelope estimates using a counterfactual world in the absence of climate change to estimate how much area would have burned in the absence of climate change. And our general conclusion is that about half of the area burned in western U.S. forest over the past 30, 35 years are a byproduct of climate change as expressed through this relationship that you see here. So the question is this a change? Is this a change in fire? And this is a 3 different data sets that I've put together that I think are the best data sets that are out there for looking at long-term fire activity over the last century for western North America. This includes grasslands and forests, etc. Is this a change, right? And there's lots of questions behind this. Is the data quality good? What's up with the early period? It turns out the earlier period was a multi-decadal drought that we actually haven't seen the likes of in terms of low precipitation. We know that also humans are playing a substantial role. We've seen widespread fire suppression really take off over the last century in the western United States, in Canada, etc. And suppression is going to be pretty successful when we have wet and cool conditions, and it's largely not successful when it's hot and dry, like we've seen more of in recent years. So is this change, right? And how do we define change? It's a difficult thing to do, right? Especially if we're thinking about some sort of complex system like fire, where fire is a function of many, many things, right? And so there are many ingredients and inhibitors to fire, and many of these are sort of associated with humans starting fires, humans stopping fires, humans modifying land cover. And what we're going to focus in on is that bottom center panel. This is a very interesting way of expressing fire danger. I don't know if you guys have something like this, equivalent to this in Australia. I think you probably do. I've seen some signs like it. But this is a really interesting way of expressing fire danger. As scientists, we could express it like that, but usually we express it with numbers. So we're going to do that today. And we know that the increase in sort of fire danger is not a phenomena that is germane to the western United States. And this is a study that David and Grant were involved in a couple years ago, but we see this at global scales. At the global scale as a whole, there's an increase in the length of the fire weather season, and you can see certainly some heterogeneity, but there are broad regions of the globe where we see increases in the length of the fire season. And of course, we have to ask ourselves how much of this is natural versus man-made, and there's some interesting attribution questions that could be asked in this realm. And what I'll do is somewhat answer those questions using a slightly different approach. So how do we define perceivable change, right? What does a change represent? You could look at the effects of climate change on fire and maybe look at fire statistics. That's certainly doable. It's challenging. There's lots of caveats. Instead, what we're going to do is actually look at fire weather. right? That's purely atmospheric. It's purely objective. It's driven by the weather. It's driven by the weather. Nothing else, not humans. Well, maybe humans are driving weather, but it's weather. So we're going to define emergence in a way from a signal to noise perspective. So the signal of climate change we're going to consider emerges when the signal of change, right, exceeds the background variability, and we're going to define the background variability as a standard deviation. Okay? And we're going to define that, we're going to define a time of emergence. What year do we see this emergence first occur? Now, the time of emergence may sound like an interesting way of putting things together. It's of use because it gives you a target timeline. Okay? And you might think of it in some ways, if you were a community and you were facing dual threats from climate change, for example, sea level rise and increases in fire activity, you might want to use something like the time of emergence to understand which of those threats is going to be most apparent, and that might be used to prioritize adaptation dollars. So we're doing this using the Canadian Forest Fire Weather Index. I know you guys don't like this one. We have our own in the United States. It's okay. It turns out that the indices are all fairly similar. So the Fire Weather Index here combines different measures of fuel aridity with the potential fire spread. That's really the weather part. And I look at 4 different measures, right? One is the number of days above the 95th percentile, the length of the fire weather season, like Grant and David have looked at, the annual 90-day FWI average during the fire season, and then the annual extremes. Okay? And the question, of course, is when and where do we see emergence of these outside of the range of natural variability? So just to show you that this is a good metric to use, this is a paper that I led earlier this year that Crystal was involved in. The Fire Weather Index is strongly correlated to burned area at broad regional scales. So the reds here are basically showing areas where the amount of area burned in a given year is strongly correlated to the Fire Weather Index during the fire season. And gray, just for reference here, are places that are either the wrong vegetation type or insufficient fire. And this relationship is most strong in forested systems, the so-called flammability limited systems or climate limited systems. Right? Not so much in sort of the non-forested systems. For example, in central Australia, it's always hot and dry in the summer. The primary driver for interannual variability in fire is biomass, and that's precipitation in the previous several years. We also know that extreme fires co-occur with extreme fire weather index, and David mentioned a study that I helped him out with looking at the Chilean fires in January of 2017, and it turns out that the most extreme fire activity that we saw co-occurred with the highest FWI in the period of record, right? This is the Camp Fire that burned a month ago in Northern California that unfortunately took on the order of 85 lives or so. We also saw the highest fire weather index in the period of record coincident with that event. Okay, so let me just walk you through basically how this works. So this is a random fire weather index. Doesn't really matter where it's from. We used 17 different global climate models, right? You don't want to use one model. It might be cherry picking. You don't want to use 2 models. We want to use a broad suite of models. We look at models from 1860, right, all the way up to 2100. We use the sort of business as usual scenario to represent the period from 2006 onward. Okay. Globally, we looked at this across all global terrestrial surfaces that were burnable, so we got rid of areas with barren or are currently ice covered, just for reference. So what we do is we define a background variability. And what we wanted to do there is we wanted to define the background variability, what it would have been like in the absence of significant anthropogenic climate change. And so to do that, what we did was basically take the data from 1860 to 1910. 50 years, a good baseline. Right? You can get that baseline out there. You can get the 1 standard deviation above and below the baseline. So that's what you're looking at here. Then what we do is we look at a 30-year average. Lots of ways to define when you see an emergent signal. We could probably all come up with different definitions for this. And what I did was I defined a 30-year average for each of the variables that I looked at, and it's a 30-year leading moving mean. And what we do is we ask when this red line first exceeds 1 standard deviation and persists for all years thereafter. And that is our time, that is our year of emergence. Okay? So just before I show you the results here, I wanted to remind you what the climate change signal looks like. This is the climate change signal a multi-model median. And for each pixel, I'm basically showing you values that correspond with the 90-day period coincident with the peak fire weather index. So this is basically fire season, changes in the fire season. So warming, of course, decreases in humidity, right? Decreases in humidity are pretty ubiquitous across land surfaces. That's not great for fire. Wind speed doesn't do a heck of a lot. Precipitation is pretty heterogeneous, but if you look at where the precipitation declines, that ends up corresponding pretty nicely to areas where you see substantial declines in humidity. And I'll point them out here because those regions are going to be regions where we see emergence pretty early and maybe even already. That's basically the Mediterranean, right? Much of the Amazon, southern portion of Africa, and then you see a little bit here in Chile as well, in Argentina. Okay, so big panel here, median date of emergence, 17 climate models, right? And we consider if less than 9, right, if less than 9 models don't emerge, then it's colored light gray. So what you're seeing here is sort of a conservative estimate of when emergence occurs based on 17 models. So 4 different metrics. The top 2 are the frequency metrics, the sort of number of days of year of high fire danger, and we'll just take a look at this. 61% of the globe shows emergence, 61% of burnable surfaces show emergence before 2050. Okay, and you can see emergence is most early, again, in sort of the Amazon, the Mediterranean region, southern Africa, as well as sort of the southern portion of South America here. Australia is, interestingly enough, not nearly as significant as some other locations, although you can see that certainly Tasmania shows up here as sort of the emergence in the 2010s, which is, according to my watch, might be now. And what's interesting as well is if you look at the bottom 2, it's specifically this bottom right one, this is sort of looking at annual extrema, and it's much weaker, right? So the evidence for climate change resulting in annual extrema are much weaker, and this is probably due to the fact when I actually define the metric, I'm looking at the signal to noise. There's a lot of noise in annual extrema, so that's pretty likely why you don't see that emerge as easily or soon. Another way to actually recast this, instead of asking what year, we can ask what level of global warming, what level of warming of the globe do we see local signature of fire weather indices emerge? And that can be important for prioritizing or emphasizing mitigation actions on climate change. So it's a pretty simple calculation. It's basically inverting the time for global temperature. But what you see here is that there are large portions of the globe where we see an emergence where for global mean warming of up to 2 degrees Celsius. Okay, and again, those are the regions that I mentioned quite a bit. But it turns out that if you go from a global warming of 2 degrees Celsius above pre-industrial to 3 degrees Celsius above pre-industrial, you get a doubling in the geographic extent of land where you see emergent changes. So that is a significant finding, and of course reinforces some of the policy decisions for acting on climate change. So just the key conclusions here. It turns out that we have perceivable increases in the fire weather at local scales, and in fact, I didn't show the figure here, but we're estimating that around 19% of burnable surfaces should have emergence by 2019. So we're 20% of the globe, more or less, should have emergence now. Okay. What's also quite interesting is that emergence is primarily driven by warming. We did a sensitivity analysis. It turns out that you get the most obvious and early emergence where you have warming colliding with declines in fire season precipitation, declines in fire season humidity. That's no surprise. There's certainly some buffering in areas where you see increases in precipitation during the fire season, and you see a lot of that sort of in the boreal system. Does this actually mean more pyrotornadoes? I don't know. We only have seen 2 of them. So I'm going to end there and field any questions that folks have.
Thanks, Bill. Are there any questions?
They're probably related. The finding that it's primarily driven by warming is a construct of the equations in the fire weather index. And the way that we did it, is that we basically calculated the fire weather index globally across 17 models. And then we did it again where we tried to basically remove the trends in each of the variables individually. And so when we remove the trend from temperature, right, which you still get all this variability, etc., you get increases in fire weather, but they're not nearly as significant. And that is potentially a construct of how the fire weather index is actually calculating evapotranspiration. That's one of the things that's in there. So I would envision that some of these calculations are going to be sensitive to exactly how these indices are calculated historically.